One bit of business before we get started. Michelle clued me into a problem we were having with the homework.
With the K's?
With the K's, yes. I tried, I couldn't even get the K's to go from uppercase to lowercase. So I've submitted a report to Cengage. Of course, they won't get back to me today because it's President's Day. But I think what I'm going to do, I also discovered one other thing when I was looking at it. The number of points in that homework are massive, which means it takes forever to finish it. You probably noticed that. So this being the day for the exam and we're on to something else, I'm just going to give everybody hundreds for this one and just let it go at that and fix the problem for the next semester. Yeah. I don't see any other way around it. Maybe, yeah, otherwise I've got to spend 8-10 hours going in there and sifting through every little bit.
Yeah, I wrote down the numbers of the questions and there was like 10 of them that were put in capital K's. It was like a lot of them. And then there would be some every now and then that would let me put a lowercase. It was weird.
Yeah, they've got a glitch in the system. So I'll fix it for the next semester and you guys get hundreds this time.
Sounds good.
Thank you.
So I heard a gasp from Michelle.
I tried to say thank you.
Okay. Chemical equilibrium. We come on, turn it on first. Get up out of the way. Historically speaking, chemical kinetics and chemical equilibrium came about the same times. If anything, kinetics was under investigation before equilibrium, but it didn't mature. Equilibrium, which then I'll show you more later, equilibrium and the concepts around equilibrium matured a lot quicker. So it wasn't until we got into the late 19th century and the early 20th century that thermodynamics was developed, and that helped spur the chemical kinetics. But we're studying chemical kinetics before equilibrium because an understanding of kinetics is useful for understanding equilibrium. So what do we mean by chemical equilibrium? It's a macroscopic effect. It's what you can observe. You can measure the concentrations of the reactants and products in a reaction. And there's Emma.
Dr. Bly?
Yes.
I just heard that the homework is going to be graded like for everyone is the same. I finished the homework, so like what does that mean for me?
I'll take that into account.
Okay, so I
just came up with this solution to the problem, so I haven't considered those who actually plowed their way through it.
Yeah, I was just wondering because I was like, oh well.
Yeah.
Okay.
I'll figure out something, maybe a bonus.
Okay. And will we have time to go over some of like the lab stuff today because you mentioned that last week, I believe?
Probably. Yeah.
Okay, because I have some questions about the lab calculations.
Okay, we can do that. You're talking about the kinetics lab.
Yes.
Yeah.
Okay.
Okay. Let's see. Where was I? Yeah. Equilibrium is a macroscopic expression of things that are going on underneath. So what we're expressing here is some type of a mathematical formula that will quantify equilibrium for individual reactions. And the recognizing that on the molecular level, activity is frantic. It's going both directions. If you've got reactants on this side and products on this side, it's going backwards and forwards at a furious pace. Even at the point that we see concentrations stabilize for all these reactants and products. Right, so that's where kinetics comes in. So you can say, all right, how fast does that happen? How fast does it get to equilibrium? And then once it's there, we don't see a change. So that's why we studied kinetics first. All right, so this is what it would look like on the macroscopic level for this particular reaction. You have nitrogen and hydrogen making ammonia, which is the Haber-Bosch process, one of my favorites. You start off with a certain amount of hydrogen and a certain amount of nitrogen and no product. And then over time, they stabilize at a certain level. And they stabilize when they reach equilibrium. They stabilize based on their coefficients of the balanced equation. So if the amount of N equals 1, then you should have 3 times as much hydrogen and twice as much ammonia. And that's what you see once the equilibrium is established. And we are talking about rates. So if we had a rate constant for the forward direction, then we'd have a rate constant for the reverse direction. And those reaction rates, whatever the rate law would be, something here, something here, whatever the rate law would be, the actual rates of the forward and reverse would be equal at equilibrium. Okay, and this is just an expression of that concept, equal rates. When we studied kinetics, we were studying at the very beginning, the initial rate. So the forward rate was at its highest because there's no competing reverse rate. But now that we're into equilibrium, we have to take into consideration that the forward rate is decreasing as the concentration of reactants is decreasing. Whatever rate law applies, is not important at this point. What we're looking at is the reverse rate is also catching up with the forward rate, and that's when you reach equilibrium. So if we have this reaction where we mix water and carbon monoxide and produce hydrogen and carbon dioxide, what would happen if you add more water to the flask? If you increase the concentration of this value? We know from our rate expressions that if you do that, if you increase the concentration of one of these reactants, then the forward reaction will increase. Okay, until the reaction rates are stabilized again. Anytime you, for 0, first, or second order, well, actually, first order doesn't fit because it doesn't respond to rates, does it? Well, the half-life doesn't. But what will happen is equilibrium will be reestablished eventually because now you have a competing return reaction. You'll increase this amount and it'll consume some more of this to make more of these, but that increasing these concentrations will increase the reverse reaction, and eventually they'll stabilize again. Similarly, if you add more hydrogen, the reverse reaction will be favored until the forward reaction catches up. Okay, so what we end up with, and I've done a little bit of reading on history, and it's really messy because a lot of this work was done when our current symbology for the elements wasn't commonly available. So they were using all kind of weird symbols for the elements. Sometimes they weren't symbols for elements, but they were symbols for compounds that they didn't realize were compounds at the time. So I'm surprised that they came up with anything recognizable. But this is the offshoot. This is the end product of the work of Wade and Goldberg to Norwegian chemists. And it's interesting when you read about these, the Scandinavian area was sort of isolated from all the crap that was going on in Central Europe. Right at this time, you had, well, let's see, yeah, the French and the British were at it. Napoleon was kicking everybody around, but they weren't messing with the Scandinavian area. So that was kind of stable. Plus they had a very active mining industry and chemists were well supported. So it's no surprise that we get a lot of developments during this time period. Advances were coming out of Scandinavia. But these two guys, they went through several iterations and published their work, and we eventually settled on giving them credit for this law of mass action, which is the descriptive equation for any reaction in equilibrium. But they started off with those weird symbols too, and I think what happened was we took their work and substituted the new symbols. So this is the end result of their work. Well, actually, I've got a few more statements. I'm stealing my own thunder. Up to this point, scientists had been describing this concept of equilibrium in qualitative terms. They were just writing out the prose. What Wade and Goldberg wanted to do was quantify it. They wanted a mathematical expression. So eventually they came up with it. Their work was, they were intimately involved with rates of reactions, which they call chemical dynamics. That's not a bad term. In physics, we call statics is where you have opposing forces and nothing moving. So you study that first, and then you let things take off running, and that's dynamics. So they were borrowing, I think, from physics terms. And with reversible reactions, this equilibrium between the forward and the reverse rates, which they called chemical statics. Okay. So since they were working with solutions, and at this time, everybody thought that you had to have a fluid phase, either a solution or a liquid or something. When two things came together, you didn't get a reaction. You know, they didn't know about solid states and heterogeneous type arrangements where you have liquid and solid intimately. But they did recognize that there needed to be an intimate mixture of the reactants before you get any action. And we even recognize today that when you mix solids, even finely divided solids, into a fluid phase, a liquid or a gas, all the activity that occurs between them is on the surface of the solid. Nothing happens inside. Unless it's got lots of little holes in it, then it's still on the surface of the holes. So I digress. But since they were working with solutions, they used the terms, whatever terms they had available for them for concentration. And for us, that's molarity. And this is the equation they came up with. Well, our modern interpretation. So when a reaction is at equilibrium, and this is our generic, right, it has a coefficient of little a, little b, little c, and little d. If we have at equilibrium, we can measure the concentrations of C and D, the products, goes in the numerator. And the concentration of each one of the products is raised to the power of its coefficient. So for equilibrium, coefficients are intimately involved in the equations, whereas with kinetics, the overall reaction has to be determined empirically. So that's the way you would write it. It's always the products in the numerator and the reactants in the denominator. And you multiply them together after their powers. And at any given temperature, the K will be constant. It will always be the same. No matter what the concentrations are, once you reach equilibrium, then it will generate this K that is constant for a given temperature. Change the temperature, then all bets are off. You got to recalculate. One other thing, these equilibrium constants here that are represented by that big K are usually given without units. And that's a practical concern because you can have a whole bunch of reactants or a whole bunch of products or a whole bunch of everybody. And once you start sticking their units in there, raising them to powers and dividing them, you can have a real mess on your hands for units. So we just leave the units off and take extra care to be sure that we're starting off with the same units on both sides that go into the equation. And then the answer that pops out will be valid. Now, if you really want the units, you can calculate, right? But they're not going to be given in any reference manual. The K values for a given reaction will not have units with them. There will be a specification though. If you're in concentration units, they're usually based on molarity. Okay, so molar C, molar D, molar A, molar B. And that works for liquids or gases. But sometimes if every reactant and product in the equation is a gas, it may be more convenient to use partial pressure, which is related to the number of moles of each one. Okay. Remember Dalton's law of partial pressure. So sometimes we use partial pressures, which would be could be atmospheres, could be anything else. And if you do that, then you get a different value K for the same reaction. But the reference manual, if you look it up, it will specify whether the units begin as molarity or some partial pressure. It'll say atmospheres or millimeters of mercury or whatever the case may be. That's just a word of caution. So be very careful with your calculations and the units will give you a problem. Okay. So we're going to have to understand some things about these equilibrium constants so that when we start manipulating equations, and as a consequence, we have to account for their equilibrium constants also when we do things to the equations. We need to recognize some rules that go along with them in the marker. If you have an expression, if you have A plus B yields C plus D, and they're their coefficients, B, A, and we have a K for that equation, which is C to the little c times D to the little d over A to the little a and B to the little b. If you, now the way this equation is written, these are reactants and those are products. But if we have to flip the equation for some reason, if we have to, let's see, we did Hess's law, didn't we? Like last semester. Okay. If we have to flip the equation, say we're adding equations together, but we have to reverse it in order to make this summation work, then the K for the reverse equation is the inverse of that K. And that just makes sense because this now would be, those would be the reactants, they'd be on the bottom. And the products would be on the top. Okay, so anytime you flip the equation, you change the products to reactants and reactants to products, and the K inverses. Or you might say K to the minus 1. That's going to be off the screen. Probably just barely on it now. Why my markers keep running out so quick? Let me see, get another one. When we multiply an equation by a factor, we've had to do that in the past, say the factor is n, what does that do to this equation? And now we're not reversing it, we're going back to the previous form. If we multiply the whole thing times an n, what does that effect have? Well, now it's little n times each one of these, right? So now we have an n times that one, n times that one, n times that one, n times that one. Okay? So we can, mathematically speaking, these are all same power markers, right? So what we can do is say that this and that everything is to the n. Okay. No arguments? Okay. So that means now the K, the new K, becomes K to the n. We just take that K to the power of n. Okay. As long as the temperature is constant, it doesn't matter what we start off with, K will always be a constant at that given temperature. Oh, let's see, I think this is, yes. Now we're going to talk about making a distinct distinction between equilibrium constant, which is always constant for any starting position in our reaction, any amount that we want to start with. Once it reaches equilibrium, the calculated constant will always be the same with a given temperature. But if we start with different concentrations here or there, it doesn't matter. Wherever you start, once you reach equilibrium, you may not have the same concentrations that you would for this reaction if you changed the concentrations and did it again. You have a different equilibrium position. Or if it's at equilibrium, and we do like we did before and add one of these components, and it shifts to compensate, then you'll still have more A than you started with, because it won't use all of it up. It'll use some of it up, it'll use some of this one up from its original, so it'll drop, it'll get lower. This one will be higher than it was, and these will be higher. But once it reaches equilibrium and do your calculation, the K value is the same. It's just now we're at a different equilibrium position. Okay. All right. These Ks will have subscripts. If we just write K, we're just saying a general equilibrium constant, or sometimes we say KEQ for equilibrium constant. just to keep from getting that K confused with some other K, like our rate law K. Some of them have special applications. Case of W is the water dissociation constant. So even in pure water, the water molecule will break up, some of them, not many, but a few, will break up into, oh, this is frustrating. Let's try this one. Will break up into hydrogen ions and hydroxyl ions. And that sets up an equilibrium. And we can write an equilibrium expression for that. Okay, I'm going to give you another rule in a minute, so don't worry about that yet. It's just that these constants have subscripts. So this will have a KW, and whenever we say KW, it's always water dissociation. When we say Ka, it's acid dissociation. So if we have acetic acid dissociating, it will release that proton and leave us with the acetate ion. That one will have a K. Solubility products. We'll look at those in a later chapter, where you get a solid that's only partially soluble. It's not completely soluble, just partially. So you'll have some solid in the bottom of your container. Some of it will go into solution. You can write an expression for that. In fact, one of our labs is going to be based on that. Formation constants for complex species. In fact, this is the one we're going to have a lab for. That one, not that one, this one. We'll get there eventually. So what we learned in this chapter on equilibrium, hold on to it. The methods that you learned in this one, because from now on, we're going to be referencing equilibrium. And then this is the one where you use partial pressures, case of P. All right. So if we do case of P, it's a similar approach, right? We have the product in the numerator and the reactants in the denominator, and the coefficients are the powers. And so that's first power, third power, second power. Partial pressures. If we wrote it with using molarity, we would do this. And by the way, those square brackets, by convention, they always mean equilibrium. Equilibrium molarity. Right? If we write these, right, then we're going to say, in fact, sometimes you should leave the parentheses out because you've already got the partial pressure expression in there. Parentheses just separate them. Usually, though, if we write one for molarity and we use parentheses, we're saying it's not at equilibrium yet. Right? And there's good reason to use that, which I'll hopefully explain later. So this is if it's at equilibrium concentrations, and if we use parentheses with molarity, it means we're not at equilibrium yet. Okay. So if we have these values in the atmospheres for each one of these components, right? Very low atmospheric values, and we write an expression for them, then we just stick those numbers in to the powers, and we end up with this value, right? 3.9 times 10 to the 4th. Right, and notice we left out the values here. All of these pressures are in atmospheres, right? So if we try to determine a unit of measure for this, we would have atmospheres to the 4th in the denominator and atmosphere squared in the numerator. So our unit of measure will be atmospheres to the -2. So just making the point, we don't use the units. We know their pressure because we know the origin of the numbers. That's important. We can relate one to the other. If you have a K value based on molarity and a K value based on atmospheres, then we can relate the two together. Right? This would be the partial pressure K, and this would be the molarity K. This is temperature in Kelvin, and the R value is the one that has atmospheres in it. So it's 0.08206, right? The very first one we learned in first semester. The part that twists students' heads around is this delta N. That's the sum of the coefficients for the gaseous products minus the sum of the coefficient for the gaseous reactants. So you say, how many moles does the balanced equation say are on the product side of gases only? And then how many moles were on the reactant side? And you subtract those. So if we take an example here, right, we had 2 on this side, but we started with 4, right? So 2 minus 4 is a minus 2, right? So you got this one to the power of minus 2, right? There's your R, and there's your temperature. You take it to the minus 2, which would be what? Square root, right? And then K's are unknown. And this is the K sub P that we just calculated. Now we know that the K is 2.5 times 10 to the 7th if we use molar units. And notice that these are all gases. So this would be a valid way to approach it, but we can convert to this if we want. Right? You can say so many moles of nitrogen per liter. Right? If you have a 1 liter container, even though they're all gases, you have so many moles per that liter. That works. Right? We learned molarity in terms of solutions. Well, this is a solution, right? Gases always form solutions. This is known as a homogeneous equilibrium. That is, all the components are in the same phase, right? They're all gas phase. These are all aqueous. Okay? So they're in the same phase. This is a homogeneous equilibrium. A heterogeneous equilibrium is one in which you have 2 or more phases involved. Okay? So this one has solid potassium chlorate, decomposes into potassium chloride and oxygen gas. Right? That's why we can take a solution of potassium chlorate and dribble it on the floor, across the lab floor, and let it dry. And then when the instructor comes in or the lab assistant comes in, they step on it, it'll go pow, because they're forcing the decomposition into this oxygen gas, and that's what shocks the foot. It's not real dangerous, but fun. And this one is also heterogeneous. Water's a liquid, and if we run a direct current through it, we can get hydrogen gas and oxygen gas out of it. Now, what do we do with those heterogeneous situations? The equilibrium expression is based upon a change in concentration to reach equilibrium. So if you look at solids, what's the concentration of the solid? It doesn't change, right? If the solid's being consumed, it stays the same concentration. It's a different amount, but it's not measured in terms of concentration because it's not dispersed through it. So we don't consider solids in the equilibrium expression, and we don't consider pure liquids either, because they essentially do not change concentration. If you want to think of it another way, if the fact that I'm telling you it doesn't change concentration plays with your mind, then say, okay, the concentration factor for these solids or liquids will be buried in the K. We look at it that way. So if we try to write this expression, we might be tempted to say K for this reaction would be KCl to the second power, and oxygen gas to the third power divided by KClO3 to the second power. These are both solids, right? So they're gone, and the only thing left is the gas. So the equilibrium constant is proportional to the cube of the oxygen concentration. In fact, if you want to know the oxygen concentration at any one time, I would say take the cube root of K, and that should give you oxygen. Okay. Now, we're going to look at these equilibrium constants in terms of what qualitative effect they have on the reaction. I think this might work. Oh, yeah, that was better. So, if we have an equilibrium constant for a reaction, we have these terms in here. We have a K for that value. I should have left this up here from before. Then, what does that K mean in terms of how far the reaction goes this way or doesn't go that way and wants to stay over here? We can do some qualitative assessments. If the K is very large, I mean huge, like that one before, 10 to the 7th. If it's really big, that means this number is really big and this one is small. So the reaction is going to be favored in that direction, massively favored. But if this value is really, really small, then it's the other way around. It favors the reactants. Okay. Now your book and some of these slides may say, all right, we're relating this to a value of 1. If it's greater than 1, blah, blah. If it's less than 1, I don't buy that. Simply because depending on the reaction, you could have powers and you could have different terms here. And you can't say that they're equal to 1 or greater than 1 or less than 1. If they're massively greater than 1, okay, then I'll buy it over here. If it's massively less than 1, that's over here. But once you get close to 1, I don't think you can say anything definitive. Okay. So a very small K means it's to the right. Wait a minute. A very small value of K means the system is mostly reactants. Yeah, small K is to the left, excuse me, to the left. And a very large K is to the right. Okay, I mentioned earlier that the convention, square brackets versus parentheses. What we do with parentheses, if we change these to parentheses, we're calculating a value that's not at equilibrium yet. Is that of any use? Well, it must be because we gave it a name. It's called the reaction quotient. And quotient because it's a divisor, right? It's a quotient. So the reaction quotient is, think of it as, this is where I'm starting the reaction. This is my starting position. And we're going to use the reaction quotient, compare it to the equilibrium constant to say, all right, which way is the reaction going to move? That's important for doing calculations later. So obviously, if the Q is equal to the K value, you're at equilibrium, which is highly unlikely, right? If you mix up a certain amount of A and B and C and D, it's highly unlikely that you'll get it exactly right. But for argument's sake, if K is equal to Q, then we are at equilibrium. That should be changed. Okay. If Q is greater than K, what does that mean? If Q is bigger than K, that means C and D are very large relative to what they would be at equilibrium. So which way is it going to move? If you got more of this than you need at equilibrium, it's going to go back the other way, right? So your system will shift to the left. And vice versa, if Q is less than K, that means that you have too little of this and too much of that, which moves it to the right. Okay. All right. So consider this reaction. In which case we've got, actually, this is one of those, mine's gone blank. Anyway, I'll think of it later. The iron 3+ ion associates with the thiocyanate ion and makes this complex. If we start off with 6 molar iron 3+ and 10 molar thiocyanate at any given temperature, we're not specifying that. And at the equilibrium, the concentration of this ion is 4 molar. This is starting concentrations. This is equilibrium concentration. What's the value for the equilibrium constant? All right. So we're going to use a technique called ICE. Let's write the equation. 3+, and these are all aqueous, right? So they are part of the equilibrium expression, the K value. We don't have to eliminate any of those. There's not a solid and there's not a pure liquid here. So we get to keep all of them. Okay. And then we produce this ion. All right. So ICE just means, what are the initial conditions? Right. This is initial. This is the change that you expect to occur from this point to equilibrium. Okay, so let's go to the next one. It should have. All right, so that's a starting concentration. Let's go ahead and put this stuff up here. I like to write it underneath the balanced equation, then that saves me a lot of trouble. So for this one, the initial concentration is 6 molar. And for this one is 10 molar. Okay. What is it for this one? 0, right? So we're starting off with 0 for that one. Okay. And this is the final concentration over here. This is actually the equilibrium concentration. Is 4 molar. Here we go. What's the value for the equilibrium constant? Well, how did this one get here? We had to add 4 molar, didn't we? That's the only way you can go from 0 to 4, is to add 4 molar of that. Right? So that means, based upon our stoichiometry, 1 to 1 to 1, we had to lose 4 molar here and 4 molar here. Right? Because they're 1 to 1 to 1. If you end up with 1 over here, you have to lose 1 of these and 1 of these. So now we can calculate, what do we have left? We have 6 molar here, and we have 2 molar here. now that we have equilibrium concentrations, we can write the K expression, can't we? So it's going to be this one in the top, and these two in the bottom. Right? Or let's see. 4 divided by 12 is 1/3, right? Or 0.333. Okay, that was a fairly simple one. We like to start simple. It's not like learn how to swim. Did your dad throw you in the deep end of the pool? No, he did. Okay, well, to each his own. All right, now that we know what the K is, then we can start with different values and answer this question. If we have initial 10 here and 8 there, 10 and 8, and we still have 0 here. What's the equilibrium concentration of this one? Well, let's erase these because they're not valid anymore. We're going to have an equilibrium with the same equilibrium constant, but we're going to have a different equilibrium position. The concentrations will not be the same. Okay. So let's see if I've got it already animated. Yeah, there we go. So in this case, we have to use algebra. So we know that with their one-to-one relationship, we're going to get some of this. We know the direction that this reaction is going to move because there's nothing over here. It has to go that way. We don't have to calculate a Q. If you're given a value over here, 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 all of these, then you might have to calculate a Q to see which way it's going to move, right? Is it going to go back this way or that way? And that affects the setup for your ice. But we know it's moving that way. So that means we're going to get some here and we're going to lose that much here. Right? Okay. So we got 10 minus X here. We got 8 minus X here, and we got X there. Right? So you would write your equilibrium expression like this, right? There's your X, your product on top. There's your 10 minus X and 8 minus X there, both to the first power, and they're equal to 0.333. So we have an X here that's our unknown that we can solve for. The question is, how do you solve for it? Well, the surefire way is to recognize that in this case, when we multiply these two together, what are we going to get? A quadratic. We're going to get an X squared and X. There's our X squared. There's our X value. So we're going to end up with this quadratic. And remember, in order to solve a quadratic, all the terms have to be on the left equal to 0. And you can use your quadratic equation. Right? If this is A, that's B, and that's C, it's minus B plus or minus B squared minus 4AC divided by 2C. Oops, how'd that happen? I accidentally pressed the button that I wasn't supposed to. There we go. And in fact, see, do I have it on this one? Yeah. I got the quadratic on the back of my calculator because I can't always remember it. Yeah, 2A on the bottom. So let's see, I messed up. Let me go, here we go. Now this way, remember when you solve a quadratic, you get 2 values, 2 numbers. Because of this right here, plus or minus. You're going to get 2 numbers. then you have to decide which one is real. If X represents this amount, right, then it cannot be bigger than 8. Because 8 would use up all of the thiocyanate. If that were the case, then this would be 8, that would be 0, and this would be whatever, 2. So if you get two numbers, then if one of them is greater than 8, throw it out. Can't be. It's impossible. Mathematically okay, but not physically. So the answer has to be 5. That's the surefire way. Eventually, I'm going to show you a trick where you can estimate, and you can make some assumptions and simplify it, so that you don't have to use the quadratic every time. But with a number this large, like that, 5, it's a substantial amount of these guys. You have to use the quadratic in this case. There's no way around it. All right. So here's another one. So if we change the values to 6 and 6, what's going to happen to the final concentration? Well, they didn't do it for us. We would have to put 6 in here, 6 in here, do the same quadratic expression and solve for the unknown, which I'm not inclined to do right now. But it can be done. Okay, so here's your steps for solving equilibrium problems. You've got to have a balanced equation because you need those coefficients. And it needs to be the smallest whole number value for your coefficients. So you write the equilibrium expression, which is the mathematical expression for the law of mass action. And you list the initial concentrations. Just set up your table like this. Once you've got your balanced equation, then you can set up your table, initial change, equilibrium, and put in the values that you do know. If you have, if all of the values here are non-zeros, you will have to calculate the Q. But if there are any zeros in here in the initial concentrations, you know which way it's moving. If there's something here, and a 0 there, you know it's going that way. Okay. Once you figure out what way it's going, then you know where to put your unknowns. In this case, if that were 0, and say this were 3, just to make up something, right? Then the X's would be what? You're going to lose some of that and lose some of this and produce some of this. So this would be an X. This will be a minus X. What about this one though? Right. For every X you produce here, you're going to produce another X, aren't you? Okay. So now you have 10 plus X, X, and minus X. And then you would set up your equation equal to the equilibrium constant. Okay. But if you have non-zero numbers in each one of these, you need to calculate Q and see which direction is it going to move. Yeah, I said that already. Define the change that's needed to reach equilibrium. What direction is it going? Try to choose X as carefully as possible. Look at the question. If the question asks for what will be the concentration of thiocyanate ion in this case, then that X is correct. Because when you solve the equation for X, you've got the answer. If you choose your X poorly, then you may have to do another calculation to find out what the answer is. If the question asks how much thiocyanate is left, then and you get X, then you're going to have to subtract X from, you're going to have to subtract X from 3, which is okay. You can do it that way. But if you choose your final X down here as some value, then you got to work back to see what these values are. It's 6 1/2 does the other. You're going to get the right answer either way. And just, you may take fewer steps if you choose your X carefully. Then you substitute your values in the expression and solve for the unknown. Okay. I'm gonna let you guys do this one on your own, right? There's several problems here based upon the value of K, and use these, and you have to calculate your Q for each one of these. Let me see, did I do it for one of them? No, just give me answers. All right, so for trial 1, these are the final answers. For trial 2, those are the final answers, just so you can check yourself. Those are the final answers. Notice that we're at different equilibrium positions because the concentrations are all different, but the K will always be the same. All right. So let's see if we can. 9:30. So we got till 10 for the lecture. Let me see how many more slides I've got here. Oh, we got some videos too. Okay, well, we'll run over a little bit, but not too far. So a 2-mole sample of ammonia is introduced into a 1-liter container. At a certain temperature, the ammonia partially dissociates according to this equation. Okay, that's our balanced equation. Nope, it's not balanced yet. So we have to balance it. All right, let's go ahead and do that. First of all, do we keep everybody? Yeah, they're all gases. So we have N2 and H2. Right? Maybe you remember the coefficients from previous examples. This is just flipped from the Haber-Bosch. It's a decomposition. So we need 2 nitrogens. Now we need 6 hydrogens. So that's balanced. We start off with initial change equilibrium. Initial 2 moles of ammonia in 1 liter. So that's 2 molar, right? And we have nothing here, like 0, 0. So we know which direction it's going. At equilibrium, 1 mole of ammonia remains. So we're still in 1 liter container. So 1 mole will be 1 molar. Okay. How do we get there? Well, we had to produce some of this. What's the question? Calculate the K. Okay. So we need values here. So we're going to produce some of this. If we got 1 mole left, how much did we use up? We used up 1 molar, didn't we? Right? So if this is 2, then half of that is 0.5, right? And since we know this is 1, then 3 times that is 1.5. So we have 0.5 molar and 1.5 molar. Now we can calculate K. Let's see, they're going to do it for us, or do we have to do it? Oh, all right. So the K equals, excuse me, N to the first power times hydrogen to the third power divided by ammonia to the second power. That means 0.5 and 1.5 cubed, and then 1.0 squared. All right, so plug it in my calculator, and it should come out to 1.69. Let's see if it does. I'm gonna cube 1.5 first. See, enter, and then just there, and then times 0.5, and then divided by 1. 1 squared is 1. 1.6875. Okay. That was fairly simple. I'm gonna leave it up there just in case. Oh, a new one. All right. Um, 1 mole of N2O4 is placed in a 10-liter vessel. So that's 1/10 molar and allowed to reach equilibrium. Calculate the equilibrium concentration of N2O4 and NO2. Let's see. We have to do it ourselves. Yeah, let's go ahead and do that. So here's N2O4 in equilibrium with 2NO2. And we're starting off with here. We're starting off with 0.100 molar of that and nothing of this. So we're given the K. Okay, so we're gonna produce some of this and lose some of that. So it wants us to calculate the equilibrium concentration of each one. So really, in this case, it doesn't matter which one is X. 6 1/2 does the other, because you're going to have to calculate the other one anyway. So let's just say we lose some of this. That means we have added twice that much, right? 1 to 2. So this is 0.1 minus X, and this is 2X. And 4 times 10 to the minus 4. 4 times 10 to the minus 4 equals this value squared. And this value first power. Okay.
This is where I insert the proper calculation for this particular reaction. So I'm going to put it up on the board again here. This is our reaction. There we go. And this is the ice table. Trying to squeeze it down so I've got plenty of room. We started off with a concentration of 0.1 molar of dinitrogen tetroxide, and of course, no NO2. So we're going to have a change. We're going to lose some of this and shift over to that side. So we're going to make this a minus X. We lose a certain amount here. And the coefficients tell us that for every one of these, we gain 2 on that side. All right. So that means at equilibrium, we have 0.10 minus X of N2O4 and 2X of NO2. So the equation, the K value is 4 times 10 to the minus 4, and that's equal to the product at equilibrium to the power of its coefficient divided by the reactant. Okay. Now that's where I stopped. That's where I stopped in the in the in-class video. But frankly, I made a mess of it for that video. So that's why I'm inserting this one. And this gives me an opportunity to offer a tool that we often use in doing these calculations where we estimate or we approximate. And it avoids the need to use the quadratic equation. So with this equation, notice that with this K value, a very small K value, what that means is that the reaction tends to be mostly over here. Very, very little of this is produced, right? So compared to this 0.1 molar, that X is going to be extremely small. So what we're going to say is that this is approximately 2x squared divided by 0.10. Okay. That effectively eliminates the need for the quadratic. And I'll show you how that works right now. Okay, so to resolve this and get our X on one side and answers on the other side, we're going to put this one over here, and 0.1 times 4 times 10 to the minus 5, this is 10 to the minus 1, so that makes this 10 to the minus 5. So we're going to have 4.00 times 10 to the minus 5 equals, square that value. So that's 4x squared. Then we'll take this 4 over here and divide it into that value. So when we do that, we get 1 times 10 to the minus 5 equals x squared. Now it's a simple matter of taking the square roots of both sides. So x equals the square root of this value. And let's see, I've already done the calculation, so let me find it. 3.16 times 10 to the minus 3, that's equal to x. So now that we know x, we can do the calculations here and here for those values. All right, so I'm going to have to erase some of it. Let me erase this much right here. Now that we have a value for x, we can say 0.1 minus 3.16 times 10 to the minus 3 is equal to the concentration of N2O4 at equilibrium. And that should come out to 0.097 molar. Then we say 2 times this value, right? 2 times 3.16 times 10 to the minus 3. And that would just be, let's see, 2, 12, 1 and 2 is 3, 6.32 times 10 to the minus 3 molar. So, in fact, it is extremely small compared to 0.1. So those are our answers. This value is the equilibrium concentration of NO2, and this value is the equilibrium concentration of N2O4. Now, there's just one, it's kind of like a rule that we go by, is when you do this approximation, you should be able to put these numbers into the equilibrium expression and get the K value, right? If these are equilibrium concentrations, you should be able to put those into the formula, and this should calculate the K value and be close to the accepted value, which was 4 times 10 to the minus 4. So if we do that, if we say K then should be equal to this much right here to the second power squared, 6.32 times 10 to the minus 3, right? That's this concentration, then squared it. And then this concentration, 0.097, is to the first power. So if we do that calculation, let's see if I've still got it in here. Yeah, it's in here. So let me square that. Where's my, here it is. So this is 4 times 10 to the minus 5, right there, divided by 0.097. And then we'll divide that value by 0.097. And we get 4.12 times 10 to the minus 4. Okay. The value that we were given for K is 4 times 10 to the minus 4. Okay, so the true value is 4 times 10 to the minus 4. The rule is this value needs to be within 5% of that value, right? So how would we calculate whether or not it's within 5%? Well, I'm going to need some space, so let me erase some of this. Okay. So how far away is this one than that value? It's 0.14. The difference is 0.12. So we want to see if this value is within 5%. So we just say, what's the difference? 0.12 times 10 to the minus 4 divided by 4 times 10 to the minus 4 times 100. Okay, so let's do that. 0.12, enter, and 4 divide, and then 100 times. That's 3%. So we are within 3% of the value. So these values are considered reliable. If you want to get closer, then there's another method that I don't have time to go into right now, but it's called the method of iteration. And what you do is you take the expression with x's in it, and you substitute for one of those x's this value. Must be these values. Yeah, you substitute these values. And you substitute one of these values. So you would substitute the smaller value where it's supposed to go, and then recalculate the other x, and you should get even closer. Right. But for now, this method where we look at the if the K value is extremely small, then this trick works pretty well. But you do need to confirm that it's within 3%. 5%. It's less than 5% difference. Okay, now back to the main video and the in-class session. Let's go on to Le Chatelier's principle. Leave that behind for now. All Le Chatelier said was that if a system is at equilibrium, and we do anything to disturb that equilibrium, and so the equilibrium must be disturbed in such a way that it changes conditions, temperature, concentrations, pressures if they're gases, whatever the case may be. The system will respond in such a way as to reestablish equilibrium. It will, with a balanced equation, then it will move from one side to the other to reestablish equilibrium. What it's trying to do is find
the lowest energy state. It's another way of looking at it. Concentration, we've looked at that before, right? If you add a reactant, it's going to shift to the right. If you add a product, it's going to shift to the left. If you remove a product, then it'll keep shifting to the right. If you continuously remove product, it's just, keep trying to catch up, moving to the right. And that's the way the Haber-Bosch process works, where you have nitrogen gas plus hydrogen gas. Hydrogen gas yielding ammonia. These are all gases. So what Haber did, aside from using iron as a catalyst, right, what he did was, as in the reaction vessel at high temperature and pressure, you continuously bleed off the mixture and you cool it down. And nitrogen and hydrogen have a very, very low boiling point. So you only have to cool it so far and they will drop right out of solution. Excuse me, it's the other way around. I'm sorry. Boiling point. Ammonia has a higher boiling point. So you cool it down just enough to drop the ammonia out as a liquid. And these stay as gases. Okay, and then you take those and you pump them back into the reaction vessel. And you just keep doing that continuously. So as you're doing that, you're removing this in an external circuit, and then you're flooding these back into the system. Okay? So you're removing that and adding these at the same time, and the system keeps trying to go that way over and over again. So after about, let's see, what is it? About five cycles, 5 exchanges of everything that's in the reactor, you get about a 15 or 16% efficiency, which is pretty good. For other reasons, it's, and we'll talk about it in just a minute. Concentration. So that's what the effect of concentration is. If you add products, you shift to the right. If you add reactants, you shift to the left. Or rather than add products, if you remove reactants, you shift to the right. If you remove products, you shift to the left. And that left-right terminology is only valid if you're referencing a balanced equation. So remember that when we do the Le Chatelier's. When you're explaining things, if you don't have a balanced equation to reference, then left and right means nothing. It could be the other direction, for all I know. Oh, I heard a person.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We filled 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
That was the effect of concentration. Changes in concentration of reactants or products. But that's not the only way you can disturb an equilibrium, right? We said before that you can disturb an equilibrium is only constant value. The K value is only constant for a given temperature. So what happens if you change the temperature? Well, the simplest way to think of this reaction is to consider whether heat is produced or heat is consumed in the reaction, exothermic or endothermic. So if you have reactants, yield products, if it's exothermic, then we're going to see heat generated during the reaction. And so we're going to see an enthalpy on that side. So what I do is add the heat term. Well, you can say delta H, you can say Q, doesn't matter. Just need some symbol to say that's where the heat is. The heat's on the product side. Right? So if this is exothermic, and you increase the temperature, then you're adding this term to that side and it shifts back to the other side. So exothermics with an increase in temperature shift toward the reactants, whereas endothermic, we'll probably figure this one out. Endothermic, the Q comes in this side. Now, you increase temperature, you're going to increase the reactants and you shift toward the products. So if you happen to know, if you're given that information in a problem, then that's easy to solve, whether it's endothermic or exothermic. Just where do you place your Q value? Now there's a more involved explanation. Actually, it's a more accurate explanation. which will come from this video. But this is sort of a, I don't know, rule of thumb that makes it easy to solve that equation.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
It wasn't quite as illuminating as I had expected. It is true. It is true that the temperature change will change the equilibrium constant. So in reality, it's not as if you've got an equilibrium constant and a reaction and you change the temperature and you add heat to it and move. That works, right? That does solve the problem. But the chemistry of the reaction is explained by the change in the equilibrium constant. Because if you increase the temperature of an exothermic reaction, you drive the reaction backwards. And if you were to do the experiment and determine the new K value, the K value then would, let's do it this way. The K value originally, well, always, is some product over reactants. Okay, so if you add this to it, it actually changes the K. When you increase the temperature, it changes the K and decreases this value. So K decreases. That's the chemistry behind what's happening. We can explain it as if we treat this as a reactable product. But the chemistry is an effect on the K because you've changed the temperature. Okay, now what happens if pressure changes? Well, what effect does pressure have on liquids and solids? Nothing, right? So if your reaction only has liquids and only has solids or only has aqueous solutions, right? Change in pressure has no effect. But if you've got gases in your vessel and you change the pressure, the best way to change the pressure without having to add things to it, one of the ways is to change the volume. Because if you decrease the volume, you increase the pressure, right? Boyle's law. Okay, so if we increase the pressure, then the system is going to react in such a way as to reduce some of that pressure, if it can. How does it do that? Well, we know that from the gas laws. If we affect the pressure, increase the pressure, how should this side change? Well, we're actually going to focus on the number of moles. So if we change this one, if this one goes up, then we're going to take the moles down. That wasn't a good explanation. If you have a reaction, let's see. If you increase the volume, let's draw a picture. So you got this piston in here. You got your reaction in here, A yields B, say, and they're both gases. Okay, so if you decrease the volume, increasing the pressure, actually it goes both directions. You're going to have a more concentrated situation, right? The reactants and products are both going to be more concentrated. So if they're equal amounts, nothing happens. But there's no way the system can respond. But if you say you have, for every one of these, you have two of those, and you decrease the volume, then what the system is going to do is try to produce fewer moles to reduce the pressure. You've increased the pressure, the system is going to try to reduce it. The only way it can reduce the pressure is to shift toward fewer moles. Or if you raise it up, increase the volume, decrease the pressure, then it's going to shift to fill that gap by going from A to 2B and make more moles of gas. Oh, sounds like an English to me, or an Indian with an English accent.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we'll look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
Yeah, that last statement is the next thing I want to focus on. So I'll leave that up there for a second. Just because you have unequal amounts of gases on both sides, if you're doing this reaction again, and you change the pressure of the vessel by adding an inert gas, that will have no effect. Because while you're changing the pressure, you're not affecting the number of moles on either side. In other words, you're not introducing one of the reactants or products. When you change the pressure by changing the volume, then you're concentrating this side more than you are on this side. Right? So 4 against 2. So this one, the concentration of this side is increasing twice as fast as that one as you pressure it. But when you add an inert gas, it has no effect. It's as if they're equal molecules on both sides.